Our next speaker is Thomas Dietterich. Dietrich is a professor emeritus in the School of Electrical Engineering and Computer Science at Oregon State University, where he joined the faculty in 1985. Professor Dietrich is one of the pioneers of the field of machine learning and has authored more than 190 publications and 2 books. His research is motivated by challenging real-world problems with a special focus on robust artificial intelligence and substantial development. He is best known for his work on ensemble models in machine learning, including the development of error-correcting output coding. Dr. Dietterich has a long record of service to AI/ML community, including the president of AAAI, president of the IMLS, and the executive editor of machine learning. Yeah, you can begin your talk.
Well, hello, everyone. So if we were face to face, I would be encouraging everyone to stand up and stretch for a moment, which I just did, because this is, wow, basically 2.5 hours of continuous detailed information. I also wanted to comment on how really excellent I found the other presentations. You know, when I was considering what to present here, I felt like there was a trade-off between doing something more on the big picture, and I thought Alan Ewell's talk this morning was really wonderful in that regard. And I share his sense that that we are maybe moving beyond statistical learning in terms of the tools we need to build good computer vision or good AI in general. That we were starting to encounter some of the challenges with statistical learning, not the statistics by themselves, we're not able to get enough data to really exercise all of the modes of variation that our systems are going to encounter in the world. But I decided to and I also really just love the talk that just finished because I think it really shows how we need to think about the long tail and the just incredible variety out there in the world. This talk is going to be about statistics and about a very specific problem that real world systems need to confront, which is just how to set alarm thresholds when you're using anomaly detection. And this is joint work with my graduate student, Silu, Alan Fern, Rishit Garapalli, Dan Hendricks, and C is also jointly supervised by Professor Debashis Mondal in the Department of Statistics. So when we are working on techniques for detecting adversarial attacks or open category classification or out of distribution instances, one family of approaches calculates some score about how suspicious we think things are, and assigns an anomaly score to that point. So when we get a query X, we run it through some kind of a detector or scoring mechanism. We get a score, and then we have to threshold it against some threshold tau. And if it exceeds that threshold, we're going to raise an alarm and say, we think this is an attack. So I'm looking at the test time evasion attacks rather than the training time or poisoning attacks. If it's less than the threshold, then we can go ahead and classify it with our classifier. Now, in practice, we have to decide how should we set tau. And one thing we could have a couple of different goals. Let me just talk about those here. So along the horizontal axis here is the anomaly score for a problem that I happen to be working on right now with the open category detection. And the vertical axis is the probability density. And the blue curve is the probability distribution or density of anomaly scores for my known categories. And then the red is for my novel categories that I did not see during training. Now, there's a lot of literature that tries to set a threshold to minimize the number of false alarms. So that would be setting a threshold here, right? And you'd bound the error under this right tail of what the anomaly scores were for your normal data, for the non-adversarial data. An alternative goal, which is the one we're interested in, is trying to set a threshold down here to bound the probability that we will miss points that are actually attacks, right? So we're trying to bound the number of missed alarms instead. Now, one advantage of trying to do the former, of minimizing false alarms, is all you need to do is estimate this blue distribution. And because you have your training data, you can use cross-validation techniques or what have you to estimate that. I'm a fan of conformal prediction, which is probably a very nice way of doing that. But if you don't, if you're interested in the red curve and bounding the tail and the tail of this red curve, well, then you have a much more difficult challenge, because you need to have training data that's labeled with these anomalies that you've never seen before. And in some sense, you just can't get that. So question is, well, can we set tau statistically somehow? If we had the, now let's consider the cumulative distribution of our anomaly scores. And if we had the CDF FA, which is the CDF of our aliens or our anomalies or our attacks, we could say, well, give me I'll set tau such that I'm capturing, 95% of the alarms, or in other words, I want the 0.05 quantile of this distribution. Now, I do note that this assumes, it requires us to make the assumption that the anomaly scores come from a well-defined distribution. That's a little bit weaker than assuming that the anomalies themselves come from a well-defined distribution, because we're only worrying about their scores. But it's still a questionable one, and one we need to keep in mind. But if we want just to define our goal as detecting 95% of the attacks, that only makes sense if we can talk about a distribution over attacks. So almost from the way we're formulating the problem, we are making this statistical assumption. Okay, so how can we estimate this CDF? Well, one way would be to collect labeled training data of these anomalies. So let's say I can get labeled training data of adversarial attacks or open category queries or out of distribution instances. Then obviously I can compute their anomaly scores, which I'll denote by SA for a sample of anomaly scores. And then I can fit an empirical CDF, and then I can choose the threshold. But of course, this does require getting this labeled sample, and that can be hard to acquire in the wild. So several people have instead suggested a more of an unsupervised alternative. And this particularly comes up in a sub-literature in machine learning called the positive unlabeled literature. But it's a slightly different setup than here. But the idea is that we can go out and collect a sample of clean data. This is the data we are training our classifier on. We can collect mixture data. And this is the idea, is to get an unlabeled sample of data that is a mix of clean data and also attacks or anomalies or open category queries, but it's unlabeled. And the thought is, well, maybe this is easier to collect. And then what we want to do is calculate the anomaly scores for those two data sets, and then estimate their cumulative distribution functions, F0 and FM. So F0 is going to be the clean data, and FM is this mixture. So M, the subscript, denotes the mixture data. And now it turns out we can get an estimate of FA by observing that the mixture distribution is going to be some mixture of the clean distribution and the anomaly distribution with a mixing proportion alpha. So if we could obtain estimates of F0 and FM, which we have, and an estimate of alpha, then we could plug into this formula and get ourselves, by solving for FA, get ourselves the estimate of FA we want, and then we could threshold it. So that's the basic plan. There's only one problem, which is that alpha is not identifiable. So it's pretty straightforward to prove that there is no way that can estimate alpha with any guarantees, like fixed sample size guarantee. But if we're willing to make some extra assumptions, we can get around the identifiability problem. And one approach is a general strategy, which is to not exactly estimate alpha, but estimate something that is a fairly tight lower bound on alpha. And the idea is the following. We're going to set alpha, our estimated alpha, to the smallest value of gamma, where we're going to vary gamma in the interval 0, 1, such that there exists a probability distribution Q such that the mixture distribution PM is equal to 1 minus gamma times P0 plus gamma times Q. So basically, we have this formula, right, that we know from the mixture assumption exists, and we want to find the smallest value of gamma that satisfies this equation, basically. So for which Q is valid. Well, what would it mean for Q to be valid? Well, here's an example, again, using the same anomaly scores that I showed you before. If you plug in different values for gamma and then compute the estimate for F hat A, the anomaly, this is the anomaly CDF here, then if you use a gamma that's way too small, right, I generated this data with alpha equals 0.25. So 25% of the data points are these adversarial attacks or open category queries. And if you use one that's too small, your estimated CDF goes way negative, right? I mean, it's down to -3. And of course, to be a valid CDF, it needs to be between 0 and 1. So the idea is we're going to gradually increase gamma until we get something that's a valid CDF that's always above 0 and between 0 and 1. Great idea, except that because of sampling fluctuations, it never happens. Even when we set gamma equal to 0.4, this curve dips below 0 here. It's just, you're subtracting two curves that are quite similar to each other, and because of sampling variability, the subtraction can go negative. So it doesn't quite work. But in an important paper by Patra and Sen in the statistics literature, it hasn't been picked up a whole lot in the machine learning literature, they propose the following strategy. They say, compute your estimate. So you get this black curve here, which is our estimate, and then apply isotonic regression. And some of you may be familiar with isotonic regression. It finds the least squares fit to the data that is monotonically increasing. And we typically have to clip it at 0 and 1 to turn it into a valid CDF. And so we'll call that F check. That's the little check sign there. And now we look at the Euclidean distance between these two curves and call that D of gamma. And the idea is that we're going to try to minimize the Euclidean distance between these two curves, or at least stop when that distance gets small enough. So in their paper, they prove that, that their estimator alpha naught, which is basically the smallest value of gamma, such that the distance between these curves is less than some universal constant divided by the square root of the sample size times gamma. So they prove that, that this is a good estimate, but they don't tell you how to calculate C sub n, unfortunately. It's one of those proofs that just says there exists a constant. It depends on the sample size, but otherwise we don't know what it is. So they propose that you draw this picture, which is we're plotting the squared Euclidean distance between the estimated F hat and its isotonized correction. Multiply that by gamma, and you get this blue curve. And then they say, well, look for the elbow in the curve, and maybe calculate the second derivative to help you find the elbow. Well, this isn't an algorithm, so it fails from a computer science standpoint. And so when I plotted my data, I didn't see any kind of elbow in my data. So I had an idea. So this is the actual little piece of novelty. It's a completely unpublished work, and it's also very tentative. But the idea was maybe we could find a resampling strategy to assess the sampling distribution between F hat and F check. And so the idea is that we could suppose that suppose that we've got the right value of gamma. If gamma were 0.15 in this case, then that red curve would be a really good estimate of the CDF. And if it's for the anomaly scores. And so we could draw bootstrap samples from it by sampling points in the 0-1 interval here, and then finding out what data point corresponded to that on this empirical CDF here. And we would get an anomaly score like this. And so we could draw, say, 100 or 1,000 of those samples, and then estimate and for each one, we could recalculate F hat and F check on these bootstrap replicates. And then we could calculate, say, the 25th and 75th quantiles of the distances. So for each bootstrap replicate, we're going to calculate this D sub B, the Euclidean distance between F hat and F check, calculate the quantiles of that, and then choose the smallest value of gamma such that the distance falls in that range. And visually, it looks like this. So these are for various values of gamma, or which are candidate values for alpha, right? These are the interquantile ranges or interquartile ranges of the distribution. And bingo, when D gamma falls inside this is right at 0.25, or right around there. So, this looks like it might be a promising estimator. There have been others in the literature, and one of the ones that I think is the best that's already out there comes from Ramaswamy, Scott, and Tiwari. And Clayton Scott at Michigan has really looked at this problem in a lot of detail, and lots of problems in its surroundings. So I highly recommend people read his papers. And what he does is basically use kernel mean embedding to address this problem. And so I don't have a lot of time to go through this, but basically he can set up an optimization problem where you can solve for this distribution by solving a quadratic program. And he gets pretty good results. This is his method is this red curve, and these are 4 competing methods. And this is the error in finding the optimal value of his mixing parameter, which is lambda. Okay, well, suppose now that I have an estimate for alpha. Now, how can I set the value of the threshold? And now I'm going back to work that was published at ICML 2 years ago by Siliu, Rashid Garipalli, myself, Alan Fern, and Dan Hendricks. And what we did was you choose a target quantile, Q, say we want to do a 0.05 for Q, and we choose as our threshold the rightmost point where the empirical, this is again the F hat sub A, our estimate of the empirical distribution, where it crosses this line. So in here it crosses it 1, 2, 3, 4, 5, 6 times or something, but the last time, that's the one we'll use to set our threshold. And then we're able to prove a theorem that says that this algorithm will return a threshold that achieves an anomaly detection rate of at least 1 minus Q plus epsilon. So we have a measurement or a sort of approximation error here with probability 1 minus delta. So a pack type guarantee, as long as the sample size exceeds this amount, which is basically big O of 1 over epsilon squared, 1 over alpha squared, log of 1 minus delta, or 1 over delta. So it has the usual 1 over epsilon squared dependence that comes from using these concentration bounds. And it relies, in this case, on a concentration bound for the convergence of empirical cumulative distribution functions to their true values that comes out of a nice paper by Massart from 1990. So now if you really want a guarantee, let's say we want a guarantee for that we will detect, say, a 1 minus, I don't know, beta of the points, and I have a certain amount of data, then I can figure out, I set beta equal to Q plus epsilon. From N, I know what epsilon has to be, so then I can choose a Q that will give me that guarantee. Well, if we don't know the exact value of alpha, any upper bound on alpha works. So you can see there's a problem. From a theory point of view, we need to know alpha exactly or an upper bound on it, but what we can get experimentally is a lower bound. So the 2 pieces of theory do not come together with an overall guarantee. But assuming we can get a pretty good estimate of alpha, I think this algorithm for choosing the threshold is a good algorithm, which we see experimentally. So let's look at experimentally. One other thing, I guess, is we've done some more recent work where we asked the question. In our previous work, we assumed that we had 2 samples of the same size. So our clean data was of size N, and our mixture data was of size N. But what if we can draw those, suppose we have an overall budget of N, but we want to use maybe different sizes for those 2 samples. What's more important? Should we get more clean data or more mixture data? And so it turns out, from theoretical considerations, we want to bound the distance between our empirical curve and the true CDF. And it turns out we can do that by bounding this. This is an upper bound on that. And we can turn this into an optimization problem. What's the best value of N sub M, the number of mixture data points, and what value of delta should we use for our confidence, given that we have an overall confidence budget and an overall sampling budget. And C was able to prove that this is a convex problem, and it remains convex even if we just focus on choosing epsilon, or choosing delta. And so then she's able to numerically solve for this, and we get the following results, that if alpha down here on the bottom is the true proportion of attacks or anomalies in your data, then as it goes to 0, the ratio, half the data points should be from your mixture data. But as it gets larger, then the fraction of points that should come from the mixture data increases until it hits 1, when all of your data is attack data. And this over here is going to be your approximation error epsilon, basically. Okay, and so then we studied 4 experimental questions. We wanted to know, if you use this algorithm for choosing tau, how good is it? The second question was, how loose is the theoretical bound on the sample size? How good are the recall and the false alarm rate in practice? And what is the impact of using an overestimate for alpha? So the first question was, how accurate is our threshold? And another way of saying it is, if we choose our threshold using this method, how big is the gap between the empirical recall, we call it recall here, but the fraction of attacks that are correctly detected? How big is that gap, and the target value we wanted, which was 0.95? And that gap is basically the epsilon in the theory. And so what we're doing across here is for different values of alpha and different amounts of data, what does it look like? So when alpha is very small, you need a lot of data to get close to the target. But as alpha gets bigger, you need less and less data. And so when alpha is at 0.5, you need relatively little data. 100 data points will suffice. So this is with some synthetic data. If we can also ask, how loose is the bound? And of course, the answer is very loose. So the way we get this plot is, this is the actual amount of data we had, and this is the amount of data that and from that amount of data, we calculate our actual observed error rate. And then we plug that into the theory and ask, well, what would the theory say we needed? How much data does the theory say we need to get that same error rate, right? And so, in practice, we have 100 data points. Theory says we need, 10,000 up to 150,000 or something like that. So there are several orders of magnitude difference, depending on alpha, between what you need in practice and what the theory tells you. So not surprisingly, the theory is loose here. In terms of recall on UCI data sets, using the isolation forest as our anomaly scoring mechanism, we see that for some data sets, we're able to really completely hit the target. For others, particularly the letter recognition and the OCR data sets, we're quite low for small values of alpha. And our false positive rate or false alarm rate is non-trivial. Again, small values of alpha tend to have false alarm rates in the 10 to 25% range, except for the cover type data set. We love the cover type data set. And finally, what's the impact on if we use a value of alpha that is too big? Even by a very small amount, what we see is that the blue dots show what happens to our recall, our missed alarm rate. It increases relatively modestly, but our false alarm rates really shoot up as our estimate of alpha goes is not tight. So to complete then, to summarize this, what I've tried to argue is that in a lot of our systems, when we deploy them, we have to choose a threshold against some kind of a score that's a score of for detecting adversarial queries or out of distribution queries or open category queries. And if we're willing to assume that the queries follow a stationary distribution and that we can model that, then we, and particularly that the scores, the anomaly scores follow a stationary distribution, then we can model the problem as a 2-component mixture model, where there's one component that's known from our known data, and then there's another component that is unknown from the attacks. And there's an unknown mixing proportion. And then I briefly described 2 methods for estimating alpha, although there are some fundamental challenges with doing that. But I think in practice, we'll have decent methods for that purpose. And then I reviewed our theory that gives PAC guarantees for bounding the missed alarm rate for detecting adversarial attacks, assuming that our estimated alpha is an upper bound on the true alpha. And of course, in experiments, we see that our observed anomaly detection results are much, much stronger than the theoretical guarantees. So this was funded by a variety of sources, including Elon Musk, a gift from Huawei, the National Science Foundation, and DARPA. And here are the references that I discussed. And with that, I'll stop and keep us on schedule.